Hi everyone, welcome at our webinar using generative design to engineer high-performant battery cold plates. I'm Gert-Jan, I'm your host for today. For those of you who might not know me yet, I'm one of the AI design engineers at Diabatix since 2018. I worked on several of our client projects and now I'm helping our clients to get integrated on Diabatix ColdStream and to use Diabatix ColdStream in the most effective way. In terms of background, I do have a background in mechanical engineering and automotive engineering. And by using this experience at Diabatix, I gained a lot of knowledge about battery cold plates, and that's what I'd like to share with you today. So topic of today will also be designing battery cold plates with generative design using Diabatix ColdStream platform. If you might have any questions during the webinar, don't hesitate to raise them in the Q&A section, which you can find at the bottom of your screen. If we do have some time left over at the end of the webinar, I will try to cover these questions. Voila. I will see if I can share my presentation. Voila. And then I'll quickly introduce you to what we will do today. So the main goal for today is that we design a battery cold plate, and we will do that in several steps. First of all, we will do some CAD preparation. So we will create a base model as input for the generative design. From this CAD model, we will go to Diabatix ColdStream, so the platform, where we basically make the setup for this generative design. Then the generative design will run. So that's basically the calculation process. Now that would take longer, of course, than the webinar. It takes longer than just a webinar to calculate a generative design. So I started the design that I will show you today also a while ago already, in order to make sure that I could show you the results as well today. So that that enables us as well to do the last step in the process, and that's the post-processing, where we will have a look, first of all, which design was created in the generative design or with the generative design tool. And most important, as an engineer, I would like to evaluate the performance. And that is all something that we can do in the post-processing step. So, but let's start with an easy overview of the case in order that you do have already a little bit of background in what we will do and what all the boundary conditions are, and then I will guide you through the workflow that you can follow to design high-performant battery cold plates. Let's start with a small assembly overview. So what you can see here is the battery cold plate as it would be if you have not a single design structure or cooling structure in it. So it's just a sheet metal formed plate covered by a non-formed plate, let's say, and on this non-formed plate there is an inlet and an outlet connection welded. You can see as well that there are some gaps in the middle that we need to take into account, and that you have some mounting points here at the sides of the battery modules, which also need to be considered, of course. So as I said, this assembly consists out of two parts, a flat plate and a sheet metal formed plate, and on the flat plate you have an inlet and an outlet, and some holes for the bolts, and you have the formed plate. In this plate, in the end, we will have the cooling structures, and it's the goal for today to design these cooling structures. And both of these are made out of aluminum, to be more precise, 6061 T6. If we then have a look, what we need to give as an input to the generative design tool is first of all this flat plate, and then the fluid region and the design region. We won't take into account any bending radii or drafts and so on in this phase. Bending radii that are coming into there because you are sheet metal forming a plate. That's not necessary in this phase. the generative design tool will automatically take this into account. But this is just giving you an overview. We will in the CAD preparation dive in on a higher level to this. Well, and then at the base plate, you also see that we have 4 battery modules. Each of them is represented by a heated wall with 112.6 watt. We do that in this case with just a heated wall representation. You could do that in other ways as well. What many people also do is that they draw a volume of their battery and simulate it as a volumetric heat source. That's also possible, but for today we will keep it with a heated wall. That's a little bit of what your preferences are. About the fluid, I need to tell you that it's just regular water, that there is 1 inlet and 1 outlet, and we apply a volumetric flow rate to the inlet of 3.2 liter per minute, and the inlet temperature is 48.0 degrees. And then let's see for the design space. So the design space is basically the place of the fluid, or the volumetric space in the fluid, which the optimizer can use to create the design. So that's where the freedom is. What's important to tell here is the design in the end will be made by sheet metal forming. We will be using generative design, and we want to have a design in the end which is manufacturable. That means that we also need to give some parameters of what is manufacturable for you, since it might differ from company A to B. Some of them do have other manufacturing settings. So that speaks for itself that you need to enter these parameters into the platform in order to take them into account, and in the end to come to a design which is manufacturable. In terms of the design, there is one constraint, and it is that the pressure loss between inlet and outlet needs to be around 430 Pascal. So it's very limited for a battery cold plate, but that's the challenge in this design, which we need to try to solve. And what we would like to have is that the temperature variation over the heated walls is minimized. So that's a little bit of information about the design. I told you already that we need to zoom in a little bit more on the manufacturing, since we need to add some manufacturing settings into the platform in order to take them into account. And for a battery cold plate, they look like this. The first of all is the RF, basically the channel width that you can have minimum and maximum, and we define that at the top of the cover plate, let's say so only this part. In this case, there is a minimal channel width of 4.5 millimeters. Again, this is measured on the top. This means that here and here, that's much wider. Maximum channel width again is 18 millimeters. That's again measured here on the top. We need to take into account some bending radii. The lower bending radii, which you can see here, is 2 millimeters. The upper bending radii is also 2 millimeters, and that's two times measured on the inside of the radii, and that defines as well automatically, of course, the outer radii, since the thickness is also one of the parameters that we need to give. Then there is an angle here that's 30 degrees, and we also need to define the height of the fluid region, which is this delta, and that's 5 millimeter in this case. Last but not least, we also need to define basically the normal of the bottom plate. So you have the red bottom plate here that's oriented in the XY plane, meaning that the z-axis is the normal. So this is a general introduction to the case already. You know what we want to do. We want to minimize the temperature variance while we have a temperature constraint, and the design that runs out, or that comes out in the end of the generative design tool, needs to be manufacturable by this manufacturing setting. settings. So that's the goal for today. And we will approach it, as I said, first of all, with doing some CAD preparations. You can do that in your own CAD program. I will be using Autodesk Inventor for that, but you can use whatever CAD file or CAD program that you have available. Out of there, we export a step file, which we import in our platform, in the Diabatix ColdStream platform. We apply all the boundary conditions over there. We let the generative design create a design. And finally, we can post-process the design and download the results. But let's start with the CAD preparation. Okay, so let's see if I can switch the screen. Here we go. So we are now in my CAD environment. What I want to show you today is how you need to draw all the structures, or how you need to draw this base plate. That's a handling that is different in every CAD program, so it wouldn't make sense to explain this to you if you're not using the same CAD file as I'm, or the same CAD program as I'm using. But what I want to show you is how the structures look like and how you need to export them in a correct way. So let's start with the base plate. That's what you can see right now. What you can see already is that we have drawn that as a volume, so really as a volumetric entity in a CAD file, as one body. And on this body, we have defined a few surfaces, four namely. Since I've said we will represent the batteries as heated walls, so of course we need to indicate somewhere where these walls are located. So we do that as all separate surfaces, and we include them as well in the step file. Second thing, or second volume that we include in this step file is the fluid region, and that's basically just the in and outlet connections and a 2D design, which is following basically the edges of the plate. You can see here, and I will explain that as well with the design region. So you a part of the fluid region will be used as design region. So you need to indicate which part of the fluid is design region, and there's a yellow region that you can see here. So this is, or this volumetric entity is indicated for the optimizer where he can place cooling structures and where its limits are. You can see that the design region and the fluid region do have the same height, and it's really important that you pay some attention to this height, since the height of the design region and the fluid region, as you need to give it as input for the design run, is the delta. So the delta that I explained in the slide deck of 5 millimeters, plus the thickness of your cover plate, which is 1.5 millimeter in this case. So 5 plus 1.5 millimeter results in a thickness of 6.5 millimeter for your fluid region and your design region. Last thing which is in there are the edges of the sheet metal formed plate, because they are not included in the design region. We know that the plate needs to be flat there, and you need to have some closing surface where you can weld or based on a chemical compound attach the two files to each other. And we also have the mounting points for the batteries. Here is also some contact surface with a base plate. So this is all excluded from the design space, as you can see if I make the design space visible again. And since that is not part of the design region, we need to include that as well as a separate solid. So there is a last solid which contain the edges of the sheet metal formed plate, which is not part of the design region. And then last thing that I haven't showed are two patches representing the inlet and the outlet, since we also need to indicate where they are located. And basically this input, so all these volumetric entities and surfaces, we need to export into a CAD file. How do you do that? In most of the CAD programs, that's the same. You just make the parts that you want to export visible, as well as the surfaces. You go to export as a CAD format. Let's save it at the desktop and give it the name webinar. And what you need to check is that you use the right protocol to save your step file, which is 214 automotive design. You simply save it, and the CAD file is exported in a step format, and the step format can be used to be uploaded in Diabatix ColdStream. Just see that I made one small mistake. I forgot to export the edges of the sheet metal form plate, so it's not included in the step file that I just saved, but that's no problem. I'll simply export it as a second step file, and I will be able to upload them separately. Voila, and I will upload it as a separate file in the platform. So let's have a look again to our workflow. We have covered the CAD preparation now, and we are now ready to upload the step file in Diabatix ColdStream and to make the case setup. Okay, so let's go immediately to the Diabatix ColdStream platform. I have logged in already to our demo company, where you can see, of course, a few of our demo projects, and the one that we are working on today is a sheet metal battery cold plate. First thing that I will start off with is go to the libraries and to the manufacturing settings, since I want to add the manufacturing settings that we will need in order to create a design which is manufacturable. Let's say for now sheet metal forming or sheet metal webinar. You need to select the manufacturing type, which is sheet metal in this case, and then we need to give all the parameters that we have discussed in the beginning of the webinar. So the minimal channel width was 4.5 millimeters, but I need to give it in meters. 18 millimeters for the maximum channel width. We have a inner bending radius of 2 millimeters, thickness of 1.5 millimeter, an angle of 30 degrees. The delta was 5 millimeters, and the orientation was the z-axis. And you simply add this manufacturing method. The good thing is I will now use this set of parameters for this optimization, but if I would return in 2 or 3 weeks, this set of parameters is added to your personal library, meaning that you can reuse this set of parameters without need to give it every time. Same can be done, it's a principle of a library, of course. Same can be done with the fan curves, pump curves, thermal interface materials, just material and fluid properties, and so on. So you really can build on your personal library or the library of your company. Good to know there is, if you start on the platform, there is already an extended library as well of manufacturing settings or material properties and so on. So that's basically the basic library. And you can add things to this library, but note that the things that you add to these libraries are only available at your company. If you work for company A and you add a material to your ColdStream account, company B will not be able to use it. We strictly respect the confidentiality, of course. Now that we have updated libraries, we can go to our project. And you see, as I said, I've submitted the case already in order to be sure that I can show you the results today. But that's for the end of the webinar. Now we will focus on creating the case or setting up the design run. And you can simply do that by adding the case. You can give it a name. Webinar, and you can choose either you want to make it design or simulation. Simulation is just a regular CFD simulation. In this case, I want to create a design, so it speaks for itself. I select design and I add a case. And then the first step that you need to do is to start the setup and upload the step file that we just have created. So let's go back to our desktop and select the file. You populate the case, and the platform will then load all the volumes and surfaces that you have created in this inventor file. The good thing is, all the surfaces will be automatically defined at the solid that they are at, so that makes it quite easy to define everything. So let's start with the base plate, which is this one. I'll turn it a little bit. You simply select it, and there is popping up a region settings window where you can define everything. First of all, per region, you need to select, is it a fluid or a solid? In this case, it's a solid. You can give it a name, and I will give it a clear name, Baseplate. And you need to select a material, which is this one. You select it. You can enable radiation if you want. It's not necessary in this case, but my colleague, Dr. Van den Beek, will, in one of the following webinars of the Diabatix Summer series, I will come back to that later on in the webinar, will give you more explanation on how to turn on radiation and what properties you need to give them. And then you see here in the region tree that for this region, there are several surfaces defined, and that are the battery cells. As I said, we will simulate them with a heated wall. And each of them has a heat generation of 112.60 watts. So I need to define it for each of them. Of course, if some of the heated walls do have a bigger heat generation, that's not a problem. You can easily vary that. Voila, so I have now set the heat generation for all these battery cells. Let's go to the second region as well, which you can see is the fluid region. So I select the region again, I select fluid in this case, I give it a name as well. And you need to say which type of fluid it is. In this case, it's just water. And you need to select, of course, a turbulence model. In this case, I would suggest to use K omega SST, but I'm quickly highlighting that there are several models available. And then if we go a little bit on a higher level to the boundary conditions, you see that there are two boundaries as well. One of them is the inlet, one of them is the outlet. And I believe this one is the inlet. And you can see again that you can define different types to these boundaries. You can select a pump inlet or a fan inlet. If it's an air-cooled case, you can just define a pressure edit. In this case, we will go for a fixed flow rate inlet with a temperature of 48 degrees, which is 321.15 Kelvin, and a mass flow which correspond to this value, and that's it for the inlet. Of course, for the outlet, if we have defined the inlet, we need to just define the pressure at the outlet, which I'll set to 0 Pascal. Okay, and then you see one more region, and that's the sub-region of the fluid. And I'll zoom out a little bit to visualize it. So this is the design region, as you can see, and you need to select as well either a general or design. Design is if it's a design region. General, why would you use a sub-region which is general? You can do that if a part of a region is a volumetric heat source. It's not the case in this case, but I'm quickly explaining it to you. But in this case, it's a design region, so I name it as well design. And then you also need to select which material will be added. In this case, again, 6061, of course. And you need to select the manufacturing type, which is sheet metal forming, and the corresponding set of parameters, which is this one. And now the optimizer will be able to take into account all the manufacturing settings. Last thing, not to forget, I didn't put all the volumetric or the volumes in one step file. I forgot about one, so I'll separately upload this one, and I will name it cover plate. And you just add the step file to it, and it will be loaded as well. From there on, it will just be added as a separate region in order to define it as well, just as you did with the base plate. So let's quickly check. And we give it a material as well. Okay, so we are ready now to submit a case. First, let's... Oh, no, I forgot about one thing. We didn't set the pressure loss constraint and the temperature constraint. So let's first do that before submitting the case. First of all, we will set the pressure loss constraint. We will do that to the inlet. And how do you do that? You just go back to that boundary. You add the target, which is a pressure loss minimization in this case, or a pressure loss, excuse me. And you set the target, which was 430 Pascal. And then the temperature variance minimization, we put that on the heated wall. So again, you go to the boundary itself, you add a target, and you select the optimization type. And you do that for all heated walls, unless one of the heated walls is not important, of course, and you only want to optimize 3 of them. Okay, so now I'm ready. So we have uploaded the CAD file, we have applied all the boundary conditions, we have applied the manufacturing settings, and told the generative design tool what the design space is. And most importantly, we have set the constraints and the optimization targets. And now I'm ready to submit a case. So I'll submit a case, and then you can choose whether you want to do that on a detailed level or a conceptual level. Detailed level will be on a very high resolution, basically to get to a finished design, very accurate result and fully manufacturable. Conceptual design will run less long and will acquire less computational resources. It will give you a good estimation on how the design will look like and what the performance will be. But it's not fully solved for manufacturability. It might be that there are some bending radii which are not taken into account, or some channels which are a little bit too wide or too small. That's you need to select a detailed design to solve that, and the resolution will be a little bit lower. But it's giving you a good idea. It's like you, as an engineer, make some sketches of a concept just to work on the idea, and later on make very detailed drawings in order to finalize something. It's the same. And you can do that either of these options, detailed or conceptual design, either with 100 credits or 85 credits. What does that mean? These credits represent the number of computational resources that you reserve for this design job, meaning that if you apply 100 to it, it will be ready faster than when you only apply 85 credits for it. Voila. So I can submit a case now, and it's sent it to the supercomputers to calculate. So let's take our workflow again with us. We have done the CAD preparation and a case setup. Generative design is running right now. Of course, it will take a while before that is ready, but I have submitted the same case already a while ago in order to be able to present the results as well to you today. So let's go back to our platform, and as you can see, I have now a case running, the one that I just submitted, and there is a case ready, the one that I submitted already a few days ago with the same parameters in order to show you the result today. So let's open it, and then you see that we are coming to the case summary, and this summary is giving you an overview of the most important parameters, as well the resulting parameters, like the temperatures on the heated walls, as the input parameters. Let's have a look. I'll put it in degrees Celsius. That's a little bit easier for me to analyze. And then you see, for instance, the maximum and minimum temperatures on the heated walls. I remind you, we try to minimize the variance over it, and then it did a very good job, since the variance over the cells is limited to less than 2 degrees, which is a very good job, especially if you take into account that only 432 Pascal was used. The constraint was 430 Pascal, so we are right on top there. You can also see some of the input parameters here. You can also see then are a few buttons on the top. You can go back to the setup. So if you have a design and you want to see in a more detailed way which input parameters were there or which constraints were set, you can go back to the setup. You can download the design, and if you click that button, a step file of the resulting sheet metal plate in this case will be downloaded. You can download the results, and you can duplicate the case. Then a new setup will be created with the same parameters and same geometry. You can then easily change one of these parameters and run the case again, so that you don't, if you want to run a similar case, that you don't need to redo the full setup. So these are a few important features when post-processing your case. Most important one is, of course, in the 3D result tab, and if you open that one, you are coming into the 3D visualization module, where you can visualize on the one hand side the design which is created. I will rotate it a little bit in order to see it, and then you can see the sheet metal plate which is created with all the features, the channels corresponding to the minimal and maximum channel width that we gave to the as manufacturing settings in the beginning in the setup. And from here on, you can also visualize the results. And you can see then that the design is added to these edges, which we have created manually. And hands-on, that you have a full cover plate created with a generative design tool. You can imagine if you would create this by hand or similar design, it would take you hours and hours of making designs, running simulations, and so on. This is done now in a fully automatic way. You just need to make your CAD file and input it into Diabatix ColdStream, give all the parameters, and you get to a final design, and you can immediately make a performance evaluation. Let's do that for a minute, since you can of course also visualize the results on here. Let's for now take the temperature. You could also visualize other parameters, but I will for now visualize the temperature in degrees Celsius. You could also do that in kelvins, and what you will see then in a second is that the base plate, which I selected in this this case, will be colored with the temperatures and the temperature distribution. That's of course what interests us in this case. You can easily take screenshots from here on. That's what I usually do. If I have finished the case, I take some screenshots later on in meetings with the team or with the management. It's very easy to quickly present them these images. You can also, for instance, visualize some streamlines. You can color them to the pressure loss or to the velocity. Let's change the scale a little bit. Voila, and you can see, for instance, where in the fluid you have high speeds and where low speeds, and how that corresponds to the solid temperature. So you have a lot of different options in this post-processing module in order to, first of all, view the resulting design, which is of course most interesting of this step, and then immediately have a look to the corresponding temperatures. Voila, so let's go back to our workflow for a minute to see what we have done. We have made the CAD preparation and uploaded that into Diabatix ColdStream. The case has calculated with generative design, and you come in the end to a high-performant battery cold plate, which was the goal of this webinar, of course. I will quickly look if there are some questions in the Q&A. I see one question of Alain, and he's asking, yeah, we optimized now the 4 heated walls, but is it possible, for instance, to apply a different weight to this heated walls? And that's indeed possible. So for instance, if you say heated wall or battery module 4 is more important than battery module 1, you can apply a higher weight to the optimization target in that or at that heated wall. So that's certainly possible. And then I'm looking for another question, and that's one of Guido. He's asking if battery cold plates can also be made with different manufacturing techniques. That can be done as well. So for now we have chosen sheet metal forming because it's used a lot in the automotive sector, but sometimes you also see battery cold plates which are made with CNC milling and so on, and that's of course also possible with this case. Voila. If there are any remaining questions, we are running out of time, but I will get back to you either by email or by phone if I have your contact details, or I'll cover them in one of the following webinars, but I'll make sure that all your questions will be answered. I will end the webinar with making a little bit of advertisement for our Diabatix summer series. Since during summer we organize some short webinars about different features in the platform, basically to get you up and running with the platform, going from classic CFD simulations to running generative design cases on very easy geometries. I organized the first webinar of that summer series already last week. If you didn't attend it and you want to follow it, you can still do that at our website. We have recorded it. Next week I will organize a second webinar where I do the post-processing of the simulation cases that I submitted in the first webinar. In the third webinar, my colleague Rejma will design a cooling jacket, so basically optimize one of the geometries that I simulated. And in the last webinar, my colleague Dr. Van de Beek will dive in more in depth about boundary conditions. So we have covered today and in the other Diabatix summer series and webinars a lot of boundary conditions already, but there are also a few more complex types of boundary conditions, and Dr. Van de Beek will tell you everything about it. So I hope I can see you again next week in the second session of the Diabatix summer series. Don't forget to register at our website like you have done for this webinar. If you have any remaining questions, don't hesitate to still ask them in the Q&A or drop me an email, and I will get back to you in person to answer them. Thank you very much for attending this webinar. It was a pleasure to enlighten you with the experience that I had in the past years about designing battery cold plates with generative design technology. I hope you learned something of it and that I inspired you to create your next battery cold plates with Diabatix ColdStream. And I would say if you have any remaining questions, don't hesitate to contact me. Thank you very much for attending, and we talk to each other soon. Bye.